Under the quiet night sky, where the stars hang like ancient memories scattered across the universe, a gentle yet profound question begins to bloom in the mind. What lies beyond the edge of the universe? It's the kind of question that stirs both smallness and wonder, as if every faint beam of distant starlight is inviting us to step just a little closer to some greater secret. Since the earliest days when humans first looked up at the night sky, that question has always been there, silent, patient, and never truly gone. It reaches into the core of curiosity, of our longing to understand the world, of our urge to know what waits beyond the boundary the eye cannot see. From the time early sky watchers imagined the heavens as a great dome filled with tiny burning points, to the age of space telescopes and satellites measuring ancient cosmic radiation, humanity has carried the same quiet awe toward the vastness above. And tonight, in this gentle journey of thought, the question returns again. Soft, persistent, luminous. What truly lies beyond the universe's edge? If the universe had an edge, would it be like an invisible wall, stopping everything in its path? Or would it open into some other realm, silent, endless, and untouched? The question is simple yet almost paradoxical, because the word edge carries the weight of old maps with borders, boundaries, and neat little lines marking where things end. But the universe is no map. Space is not a flat surface lying still. Time is not a river with two banks. And the more we think in those familiar terms, the more one truth becomes clear. To understand what might lie outside, we must first understand the nature of what lies within. The journey ahead is an exploration of the universe's farthest frontiers, cosmic frontiers, limits, destiny, and origin, where the boundaries of human knowledge brush up against the vastness of space. These limits are not barriers to fear, but doorways into deeper questions. They are the places where light has only skimmed a tiny fraction of the unknown. The places where the universe's early youth left faint traces in the form of cold, ancient waves, and the vast, interconnected regions where galaxies gather into magnificent webs before dissolving again into expanding space. Each of these is a slice of a much larger picture, and when enough slices are pieced together, we can begin to sense what might wait beyond. When thinking about the original question, the imagination might drift toward an image of a cosmic shoreline, some cliff at the edge of night, where everything suddenly falls away into darkness. But reality is stranger, softer, and far more intricate. The universe may have no edge at all in the ordinary sense. Space was not built like a room with walls. It is not a sheet with margins. Modern cosmology suggests the universe may be infinite and flat, or finite yet without a beginning or an ending, much like the surface of a sphere, but unfolding in 3 dimensions. In these possibilities, the question, what lies beyond the edge of the universe, transforms into something subtler. What lies beyond our ability to observe? What lies in regions where even light, after traveling tens of billions of years, has not yet reached us? What is happening in places forever pushed beyond our grasp by the expansion of space? To step further into that question, we must touch the idea of the universe's destiny, how it was born, how it is evolving, and how it might one day end. When we look at the night sky, we are not seeing the present at all. We are witnessing the past, moments whose light left stars millions to billions of years ago. From those scattered bits of ancient starlight, we build models of the universe's origins, of dark energy's nature, of the fabric of space as it stretches wider. As the universe expands, our horizon shifts. As galaxies drift apart, the boundaries we imagine as fixed slowly move outward. And in this widening space, the idea of an edge becomes less a physical structure and more a reflection of the limits of human perception. From here, the question is no longer mere curiosity. It becomes an invitation to explore the chain that links cause and effect, origin and destiny. Whatever lies beyond the universe's edge might connect to whatever existed before space itself began. It may relate to cosmic inflation, to other bubbles of space beyond our own, or to regions that expansion has carried out of reach of any light we will ever receive. In every possibility, the question is not just about distance, it is about meaning. And that is why this journey does not seek an absolute answer. Instead, it invites us to drift with the universe's open-ended stream of thought. In this journey, limits become stepping stones to deeper view. Destiny becomes a doorway into imagined futures, and origin becomes an anchor for understanding the present. Thinking this way, the night sky stops being just darkness. It becomes a living map, unfolding into countless paths. And at the end of each path, whether we reach through telescopes or through imagination, something is always waiting to be discovered. In the stillness of this moment, the question, what lies beyond the edge of the universe, does not need to be answered quickly. It only needs to float gently through the mind, like a small boat gliding across a perfectly quiet lake, guiding us softly into the next chapter of our endless journey through the cosmic frontiers. From the hazy yet vast question of the universe's edge, our thoughts naturally drift toward a deeper idea that to know what lies beyond, we must first understand what lies within the portion humans can actually see. And as we step through the first doorway of cosmology, a gentle but profound concept comes into view: the observable universe. Not the entire cosmos, not every stretch of space expanding into the unknown, but only the region from which light has had enough time to reach us. Within this quiet boundary, the next chapter begins to unfold, slowly, softly, like a wave of light gliding through still space. The observable universe might sound like a technical term, but in truth, it is much simpler. It is the region whose signals, mostly light, have had enough time to travel from where they originated to Earth since the universe was born. The universe is about 13.8 billion years old, which means the most ancient light we can receive has been traveling for that long. Each beam, faint almost to the point of disappearing, carries with it stories of ancient galaxies, of cosmic expansion, of those early, trembling moments when the universe had only just begun. The strange thing is that when we look up at the night sky, we are not seeing the present. We are looking into the past, into layers of time stacked upon one another, like the rings inside the trunk of an ancient tree. But the distance that light has traveled is not simply 13.8 billion light years. The space between us and the places where that light originated has not remained still. Ever since the moment that light began its journey, space has continued stretching, pulling everything apart. Because of that expansion, even though the oldest light is 13.8 billion years old, the region containing those galaxies has been drawn much farther away. When we account for that expansion, the radius of the observable universe today is not 13.8 billion light years, but roughly 46.5 billion light years. Not because the light traveled faster, but because the space between points expanded during its long, patient voyage. We can imagine the observable universe as a vast bubble surrounding us, not because Earth holds a privileged position at the center, but simply because light happens to be converging upon the observer's location. If we stood in any other galaxy, the bubble around that observer would have a similar radius. This helps us understand something comforting. Our position is not special. We are simply observing from where we stand. Everywhere in the universe, if another intelligent being were to look up at its own night sky, it too would see an observable universe shaped by the light that has finally reached it. That image creates a strangely soothing feeling that every conscious creature in the vastness of space stands at the center of its own sphere of awareness, and each bubble, whether overlapping or not, is a small window into the distant past. The universe itself may be far larger, perhaps even infinite, but what we know is only this small portion, a region where light still loses to the universe's age. Yet this limitation does not diminish wonder. Instead, it offers a kind of restful space for imagination, like a forest whose edge we can see, while knowing that deeper paths remain untouched, waiting in silence. The observable universe is not a physical border. There is no wall separating us from the rest, no boundary line marking where things stop. Only the limits of information and time exist here. Beyond that 46.5 billion light-year radius, there may be galaxies, clusters, and cosmic webs weaving patterns we will never see, simply because their light has never, and may never, reach Earth. And yet, they may be out there now, forming stars, swirling, glowing softly in their own distant darkness. That idea is both beautiful and bittersweet, like knowing there are chapters already written that our book simply hasn't opened to. The remaining pages, whether they exist or not, lie beyond the reach of our current understanding. But that uncertainty is part of the universe's charm, like a story that never truly closes. Within the boundaries of the observable universe, light is our most loyal companion. It carries news from faraway galaxies, from newborn stars, from explosions, collisions, clouds of dust, and crystals of frozen vapor drifting through deep space. Every tiny photon is a messenger crossing time itself, arriving to tell us a fragment of a much greater story. That story begins in the chaos after the Big Bang and branches outward into the hundreds of billions of galaxies we glimpse only with the help of our most delicate scientific instruments. Another quiet wonder is that the boundary of the observable universe is not fixed. As time moves on, light from once distant places continues to arrive, and the bubble slowly expands. Even as the universe stretches apart, those patient rays from long ago drift through billions of years to finally reach us. That boundary grows little by little, creating the feeling that we are exploring ever-widening circles on an endless map. And in thinking about this limit, we begin to sense that understanding the observable universe is the first step toward understanding the far larger boundaries our journey is about to cross. The limits of light are only the first wall. Beyond them lie the walls of time, of physics, and of human imagination itself. But to continue exploring what might lie beyond the edge of the universe, our grasp of the visible part, humble as it is, becomes our essential foundation. With that realization, our thoughts drift gently to a new question. If this is the limit of what we can observe, then what does that boundary look like? Is it a wall of light, a mist of time, or a fading line where brightness slowly dissolves into nothing? That question leads us to the next layer of the journey, where the cosmic horizon appears like an invisible embrace surrounding humanity's field of vision. There, in that quiet boundary, the unseen begins to flow into the story, opening soft, breath-like reflections of the regions where light has never passed. As we picture the observable universe as a growing bubble of light expanding with time, our thoughts drift naturally toward the next question, one that feels like a doorway connecting layers of understanding. If we have a visible range, then where is the final boundary of that range? Where is the faint line where light stops, where information has never had the chance to arrive? From that question, the idea of the cosmic horizon appears, not as a rigid wall, but as a delicate boundary woven from the nature of time and the speed of light. As the observable universe blooms outward like a vast sphere, the cosmic horizon forms its outer shell, the thin, hazy edge no light can pierce. The cosmic horizon is the farthest limit humans can observe, not because something blocks our view, but because light from regions beyond has simply never had time to reach us. Nothing material forms this boundary. No gas, no stone, no veil separating one side from the other. Everything is bound only by the speed of light, the fastest any information can travel in the universe. From the first instant the cosmos came into being, light began streaming outward, and ever since, only the regions close enough for its rays to finally arrive have appeared within our sight. The farther regions remain wrapped in the quiet darkness of delay, like rooms in an endless house whose doors have not yet been opened. Over billions of years, light from distant galaxies has crossed unimaginable distances. But while light moves forward, space itself continues to stretch. The gaps between galaxies widen, making the journey harder. So even though the first light left its birthplace long ago, the region that emitted it has been carried far beyond where it once stood. In the end, we are left with a boundary that light has just barely reached, the cosmic horizon. Inside that line lives the story of billions of galaxies we can trace with our telescopes. Beyond it, everything rests in the stillness of information that has not yet arrived. You can imagine the cosmic horizon as a colossal sphere surrounding Earth. But unlike a stone surface or the surface of the sea, this boundary is completely invisible. It does not shine, it does not reflect, it leaves no mark on the night sky. It is nothing more than a distance, the farthest that light could have traveled in the lifetime of the universe. And what's fascinating is that every observer, every galaxy, every planet has its own cosmic horizon. Each one is roughly the same size if the universe is uniform, yet each exists as an overlapping sphere centered on its observer. The universe has no central point, and the cosmic horizon is not a fixed place in space. It is a limit of knowledge, not a limit of existence. When we think of the cosmic horizon, it's easy to picture a dramatic, solid boundary, but in truth, it is far more fragile. From our perspective, it feels like the border of awareness, the place where everything we can know comes to a gentle stop. But from the universe's perspective, nothing changes when crossing that line. Galaxies continue to drift, matter continues to interact, energy continues to move. Everything goes on as usual. Only the light from those regions never finds its way to where we stand. It is like standing on a hill and seeing only part of the valley. The rest remains, simply hidden behind the curve of the Earth. The horizon's invisibility gives it a strangely calming quality. It reminds us that humanity holds only a small fragment of the grand cosmic picture. In the darkness beyond that boundary, there might be billions of galaxies, each containing billions of stars, each star possibly holding worlds of its own. There might be civilizations out there whose light will need billions more years to reach us, or civilizations long gone before their first signals could complete the journey. We cannot know, and we cannot be certain. Yet that unknowing does not inspire fear. It feels instead like standing before a quiet ocean at night, knowing the waves continue far beyond the darkness we can see. In cosmology, the cosmic horizon is not just a boundary of distance, it is a reminder of the limits of observation. No matter how powerful our telescopes become, they can only see as far as the horizon allows, no farther. This has led scientists to wonder, if light cannot guide us past that line, might there be other messengers that can? Perhaps gravitational waves from the universe's earliest moments, or ancient neutrinos carrying clues from a time before light could even exist. These questions open longer journeys, but for now, the cosmic horizon remains a simple yet poetic truth. It is the border between what has been illuminated and what still lies in cosmic shadow. Reflecting quietly on this, the image of an invisible wall surrounding our view becomes a symbol of dialogue between the known and the unknown. It is not a wall meant to divide, but a faint outline where imagination begins. Inside, we have data, measurements, nebula maps, and galaxies arranged across our charts. Outside, we have unanswered questions, unlit spaces, and possibilities that stretch without limit. And it is precisely that boundary that creates the beauty of exploration. There is always something just beyond reach. From this idea, our thoughts drift softly toward what might lie beyond that horizon. Not to answer it now, but to prepare ourselves to step into the deeper layers of the journey, where this invisible boundary is not an ending, but a thin mist hiding stories older and wider than anything we've seen. And from here, the first quiet images of distant, unknown realms begin to open, flowing like a slow current that carries us toward the next limits of light, of time, and of the universe itself. As we imagine the cosmic horizon as an invisible wall where light quietly comes to a stop, our thoughts drift naturally toward something deeper. If there is such a limit to what we can observe, could there be a true edge of the universe beyond it? Might space end somewhere? Like the shore of an ocean or a stone wall dividing two worlds. Humanity has carried this question for thousands of years, ever since ancient civilizations first looked up at the sky and pictured the universe as a closed dome. But as science has unfolded new layers of understanding, the idea of a cosmic edge has slowly dissolved into the vastness of space. And here, in this gentle moment of reflection, we begin touching the true nature of that question. The idea of an edge of the universe feels natural, because nearly everything we encounter in daily life has a boundary. A table has its wooden rim. An island is outlined by its shoreline. A forest has a place where trees stop growing. We are so familiar with physical limits that we instinctively imagine the universe must also have a border, a final line beyond which one might fall into darkness or enter some other realm. But the universe does not behave like our everyday intuition. Space is not an object. It is not a wall, nor a surface with borders. Space is the underlying fabric of reality, a soft yet resilient lattice where time and matter intertwine, where every motion is etched into its continuous expansion. When we say the universe has no edge, it does not mean the universe is small or confined. In fact, it may be so vast as to be infinite. If the universe is flat and extends without limit, it stretches endlessly in every direction, never arriving at a material boundary. One could travel in a straight line for trillions of light years and never encounter anything resembling a wall. Space would simply continue, like a perfect plane without an end. In such a universe, the idea of an edge makes no physical sense. Yet even if the universe is finite, it still may not have an edge. This is what often feels strange at first. and also what makes higher dimensional space so beautifully elegant. A finite universe could resemble the surface of a sphere. That surface has a limited area, yet no beginning and no end. You can walk across it forever and never reach a boundary. Our three-dimensional universe could behave the same way. Finite but unbounded, limited in volume yet without a physical edge. If one could travel far enough to loop around space, they would eventually return to their starting point, without ever encountering a wall. This leads to a soft but profound realization. The edge of the universe is not a barrier of matter, but a limit imposed by the only thing truly constrained: light. We are stopped not by walls, but by time. The cosmic horizon marks the farthest distance light has managed to travel to us, not the farthest distance space extends. There is no precipice to fall from, no cosmic cliff to fear, no curtain to lift. There are only regions so distant that even light, fast as it is, has not had enough time to reach us. If someone imagined themselves traveling through space toward the edge of the universe, they would never encounter a sign of an ending. No matter how far they went, they would still be within familiar three-dimensional space. The only thing that would change is what they could see. Galaxies would gradually fade, their light stretched redder and redder, until finally disappearing from view. But this is not because they reached an outer boundary. It is because they entered a region whose light, from Earth's perspective, has never arrived. In other words, they would not be leaving the universe at all. They would merely be entering territories beyond humanity's current reach. This truth is both astonishing and strangely calming. There is no cosmic abyss waiting for us, no towering wall to limit our path. Space simply continues, quiet, mysterious, unhurried. The only thing that keeps us from knowing more is the limit of light and the age of the universe itself. And that brings a gentle sense of comfort. The universe is not a sealed box, but a boundless ocean, carrying on in its own serene way. Every modern cosmological model reinforces this view. Whether the universe is flat or slightly curved, infinite or finite, large beyond measure or even larger still, they all show the same thing. There is no physical boundary dividing here from there. There is no evidence of a material edge, no sign that the universe sits inside a larger container. Space is everything that can exist within the context of our universe, and anything beyond that, if it exists at all, must be explored through frameworks far broader than the simple notion of an edge. Once this idea sinks in, our feeling toward the universe changes subtly. It shifts from a finite shape to a soft, continuous expanse, where every direction holds the same quiet immensity. There is no center from which to measure, no border to reach, no faraway place where space abruptly ends. The universe becomes like an invisible tapestry, woven from strands of space-time stretching endlessly, and we are merely standing on one tiny point of it, looking upward and wondering about the places where our eyes cannot follow. In this calm understanding, the question, does the universe have an edge, no longer brings unease. It becomes a gentle reminder that the only boundary we face is how long light has been traveling. Everything else continues, spreading, evolving, unfolding past our sight. And from this peaceful clarity, our thoughts drift toward deeper mysteries. If there is no edge to space, then what marks the turning point from the universe's first light? What creates the veil between its opaque beginnings and the clear, glowing cosmos we see today? That question carries us to the next step in our journey, toward the ancient light, waiting to tell the story of the universe's dawn. As the idea of a universal edge slowly dissolves into the vastness of space, our thoughts drift to a deeper layer. If the universe has no physical boundary, then what is the earliest landmark we can ever reach? If space does not end, then what marks the beginning of light, of information, of everything humans are able to observe? It is at this invisible threshold that the cosmic picture reveals a different foundation, gentler, older, and quieter than anything before. It is the first remaining light from the dawn of the cosmos, the cosmic microwave background, or CMB. And within that ancient glow, we do not find an edge we can touch, but a cold whisper of time itself, soft as a breath lingering after the universe's earliest dream. The CMB is often described as a faint, glowing screen surrounding the entire observable universe. Not bright like a star, not silky like starlight reflecting off nebula dust, but a thin wash of microwaves spread evenly across all directions, like a delicate fog draped over the whole cosmos. This glow does not shine from a single place. It is a quiet backdrop behind the entire sky, an omnipresent foundation woven into every cosmological measurement. No matter where we look in the night sky, the same microwaves are there, gentle, silent, at a temperature of just 2.7 Kelvin, barely above absolute zero. To peer into the nature of the CMB is to look back on a remarkably special era. Around 13.8 billion years ago, the universe had just been born, dense and bursting with energy. In those first moments, matter and light were inseparable. The cosmos was so hot that electrons and protons could not join to form atoms. Light scattered constantly, trapped in a thick fog of charged particles. Not a single ray could travel far without being knocked aside. In that era, the universe was completely opaque, like a deep ocean of glowing particles where no light could escape. But after about 380,000 years, the universe cooled enough for electrons and protons to unite, forming the first hydrogen and helium atoms. And when that happened, light was finally set free. Photons were no longer imprisoned in a sea of charged particles, but began traveling across space on their own. This moment, called recombination, was like a cosmic mist suddenly lifting, releasing the universe's first light to drift outward forever. Over billions of years, as the universe expanded, that light stretched, weakened, and softened into the microwave radiation we observe today. The CMB is not just a dim background glow. It is the oldest light humans have ever seen. No signal from earlier times can reach us, because before recombination, light simply could not get out. That makes the CMB a natural barrier, not a physical wall, but a temporal one. The farthest edge of sight based on light itself. Everything that happened before that moment, no matter how significant, remains cloaked in darkness. We know of it only from mathematics, theory, and the delicate fingerprints it left behind. To imagine the CMB is to picture an ocean of quiet light surrounding all of cosmic space. But what makes it truly miraculous is not just its age, it is its astonishing smoothness. Though it spans the entire sky, its temperature varies by only a few parts in 100,000. These tiny fluctuations, faint as a whisper, eventually grew into the entire structure of the universe. Galaxies, stars, planets, and everything that exists. Without those subtle ripples, the universe might have remained a smooth, uniform glow forever. Without form, without clusters, without worlds. Another curious truth: this ancient light belongs to no galaxy. It is not emitted by stars or planets. It is the faint, primordial memory of space itself, a background woven between the universe and nothingness. and there is something soothing in that thought. No matter which direction we turn, we touch the same ancient light, as if the entire universe has been breathing in unison since the beginning. The CMB is also one of the strongest pieces of evidence for the Big Bang. Its existence confirms that the universe was once unimaginably hot and dense. Without such a beginning, this soft, uniform glow would not be spread across the sky in every direction. Each CMB measurement is like a small fragment of the story of how space was born. Even its tiny temperature variations tell us about the early expansion rate of the universe, the types of energy present, and the giant waves that rippled through the cosmos long before galaxies formed. When we let these ideas drift through the mind, the CMB becomes a kind of time-woven blanket, thin as mist, yet carrying the entire childhood of the universe. It is not bright, but serene, not dazzling, but steady, not close like sunlight, but far more encompassing than any ordinary light could ever be. And in that quiet, a deeper question emerges. If the CMB is the oldest light we can possibly see, then what lies before it? What exists beyond that wall of the past? Why can't light reach us from earlier times? And is there any way, any messenger at all, that could let us glimpse the universe's very first moments? This question opens the door to the next part of our journey, where the limits of light give way to what scientists call the unseeable era, a deeper region of the past. From this ancient, faded glow, our thoughts drift toward the idea of a true temporal boundary, one that light cannot cross, but other kinds of signals might. A boundary that may hold the story of the universe's very first heartbeat. As the image of the universe's oldest light, the cosmic microwave background, slowly sinks into thought, a gentle feeling spreads. If this is the oldest light that has ever reached us, then what lies behind it? What exists beyond that veil of microwaves in the moments even younger than 380,000 years after the Big Bang? The question opens softly, revealing a new horizon, not a spatial one, but a temporal horizon, where light can no longer serve as our faithful storyteller. And from this quiet desire to step deeper into the past, the idea of a wall of the past emerges, a soft but impenetrable boundary that light can never cross. The CMB, though made of faint microwaves, gives us the oldest picture of the universe that light can offer. But at the same time, it becomes a kind of curtain, a natural boundary that prevents us from seeing further back into the universe's earliest days. Before the CMB formed, the cosmos was not a calm sea of neutral atoms and freely traveling light. It was a dense, blazing realm of energy, so hot that electrons and protons could not join to form atoms. Light in that era behaved like a voice lost in a room filled with heavy fog. It scattered endlessly, pushed back and redirected in every direction, unable to escape. The early universe was a glowing ocean of charged particles, making it impossible for any photon to travel more than a tiny step before being caught again. This is why everything before the CMB belongs to what scientists call the opaque era of the universe. Not opaque in a poetic sense, but literally. Light could not travel. No photon survived long enough to carry information from that time to us. That is why, no matter how powerful our telescopes become, no matter how many ingenious wavelengths we use, we still cannot see through that barrier. The CMB marks the farthest surface light can take us, a horizon in time that even the strongest human instruments cannot cross. If the CMB is like a thin sheet of silk, then the wall of the past is its hidden underside, completely invisible to ordinary light. Everything behind it still exists, still unfolds, still belongs to the universe's story, but light cannot bring that story to our eyes. The world before this moment is like a sealed opening chapter, leaving us only with the pages beginning from chapter 2. This wall is not a stone barrier, not a sharp line, but a soft limit born from the very nature of light. This picture helps us understand that the universe holds boundaries, not just in space, but also in time. Before the universe was 380,000 years old, everything that happened lies beyond the reach of light itself. The first photons we detect today cannot tell us what occurred within that hidden interval. In a gentle sense, the CMB is the first doorway through which light began its role as narrator. Before that, the universe's story, though full of monumental events, remains silent to us. So when we gaze at the CMB, we are truly looking at the past limit of the observable universe. Not the limit of what has ever happened, but the limit of what light can tell us. The CMB's pale orange glow, visible only when translated through scientific instruments, forms a tranquil halo around the entire sky. Each dot in its temperature maps marks a minuscule variation, a tiny ripple in the baby universe when it was only about 1% of its present size. Every one of these hot and cold spots is like a faint memory, a breath left behind by a universe still in its infancy. When we look at the CMB map, we are touching the farthest boundary of sight. We are seeing the moment when light was first freed, and at the same time, the last moment from which light can carry information about the opaque era. Beyond that horizon, light is completely silent. No photon from before that time has ever reached us. This forms a natural yet beautiful limit. We know where light stops, and we know that beyond it lies a region of the past accessible only through other ways of listening. Thinking about this wall of the past does not feel like being blocked. Instead, it feels like standing before a frosted window, aware that life continues behind it, yet only glimpsing its presence through the faintest glimmers. The universe does not hide these moments out of indifference, but through the gentle rules of physics. Light can only begin telling the story from the moment it is free to travel. Before that, the story continues, but written in signals our eyes were not made to perceive. This idea brings us to a deeper question, one that has touched the minds of many cosmologists. If light cannot cross the wall of the past, might there be other messengers that can? Ancient gravitational waves? A primordial background of neutrinos? Subtle imprints left in the universe's large-scale structure? Such thoughts lead to the next part of our journey, where humans begin searching for ways to move beyond light, not by breaking physical limits, but by listening for the other echoes of time. Yet for now, the wall of the past remains a soft horizon around the imagination, like the first thin mist at the universe's dawn. As we picture the CMB as an ancient curtain draped across the entire observable universe, a natural and quietly irresistible question arises. If this curtain is the farthest boundary light can take us, is there any way to see beyond it? Could there be messengers not limited the way light is, signals capable of carrying stories from even earlier moments, from an age before the universe grew transparent? From this desire to reach deeper into time, the idea of going beyond the CMB begins to unfold like a new path, one where light is no longer the only narrator of the early universe. The CMB is the wall of the past for light, but not for every signal in the cosmos. When the universe was very young, long before photons were freed, other waves and particles formed and began traveling in ways light never could. Some particles barely interact with matter at all, slipping out of the hot plasma with ease. Some waves weave through space untouched, unscattered, unhindered. If light was a voice muffled inside a fog-choked room, these signals were like faint echoes that managed to slip through. Faint, but possible. Among these messengers, the most striking are ancient gravitational waves, tiny ripples in the fabric of space-time itself. These waves are believed to have formed in the universe's first moments, during the burst of rapid expansion known as inflation. Unlike light, gravitational waves are unaffected by the charged particle ocean of the early cosmos. They are never bounced back, never scattered, never trapped. If they were created, they could have traveled freely from the very beginning, passing through the opaque era and carrying the purest possible information from the universe's birth. But these primordial gravitational waves are incredibly faint, so delicate that our current instruments can barely sense their presence. They are like echoes from an impossibly distant age, whispering across the vastness of space and fading as they travel. Scientists search for their traces not with eyes, but by studying the subtle polarization patterns in the CMB itself, faint signatures that ancient gravitational waves might have left, like ripples on still water. But so far, no unmistakable evidence has emerged. This does not diminish their promise. Instead, it turns the search into a long, gentle journey. Another messenger capable of crossing the wall of the past is the cosmic neutrino background, or CNB. These primordial neutrinos were released only about 1 second after the Big Bang, much earlier than light. Because neutrinos have incredibly tiny masses and almost never interact with matter, they could glide through the early plasma without being stopped. They are like quiet travelers, leaving the earliest universe and drifting through space all the way to the present day. If we could observe the CNB, we would peer far deeper into the past, beyond even the oldest light. But detecting these ancient neutrinos is extraordinarily difficult. They barely interact with anything at all. Billions of neutrinos from the Sun and other cosmic sources pass through every human body each second without leaving a trace. Detecting the CNB, whose neutrinos are far lower in energy, is like trying to hear a single grain of dust falling during a hurricane. Scientists have proposed daring theoretical designs and imaginative approaches for capturing such a signal, but turning those ideas into reality will likely take generations. Even though ancient gravitational waves and the CNB may hold information from beyond the CMB, for now they exist mostly as possibilities, soft hints on the horizon. Their signals lie beyond our current ability to observe directly. But this does not discourage us. Instead, it creates a space where imagination and science walk together, brushing up against the farthest limits of human perception. We know that behind the wall of the past lies a vibrant era, a universe filled with wild physical behavior, with energy and space-time twisting through intense primordial motions. But light cannot take us there. Until the other messengers speak, the CMB remains the final boundary accessible through direct observation. To imagine the CMB as the last curtain in a grand cosmic theater is not romantic exaggeration, it is a faithful description. The play began the moment time itself began, moving through the dramatic expansion of inflation, through the formation of matter and energy, until the curtain lifted with the release of light. Everything we can see, with our eyes or with telescopes, exists in the scenes after that curtain rose. And although we can picture the drama unfolding behind it, those early acts remain held in a gentle darkness. For now, the CMB remains the final backdrop of the universe's directly observable story. Everything beyond it lies outside the reach of light, though never outside the reach of human curiosity. And from that realization, our journey opens outward once more, toward the grander cosmic structures where the universe does not just tell the tale of its earliest light, but reveals the massive networks of galaxies, the vast cosmic filaments, and the immense voids. These structures, in their own way, are echoes of those first ripples, carrying clues about the nature of the universe that we continue to pursue with patient wonder, as the idea of messengers that can slip beyond the CMB, those ancient gravitational waves from the earliest moments, or the quiet relic neutrinos drifting through the cosmos, slowly dissolves into thought. Awareness opens into a new kind of space. Behind that veil lies an era that light itself cannot recount, yet the traces imprinted onto the universe's present-day structure still carry the faint echo of that primordial time. And if we cannot peer through the wall of the past using light, we can look instead at what today's light reveals: immense forms stretching across billions of light years. From here, the journey glides softly from time into space, from the universe's first instance into its grandest known architectures. This is where the cosmic web begins to appear, like a skeleton of light, delicate yet vast. On small scales, the universe seems chaotic. Stars scatter across their galaxies in ways that feel almost random. Even whole galaxies appear to float freely in an enormous expanse, each carrying hundreds of billions of stars. But when the view pulls farther back, beyond millions and then hundreds of millions of light years, a hidden order comes into focus, a structure far larger than anything in human experience. At this scale, the universe no longer resembles a sparse emptiness sprinkled with galaxies. It becomes a living network, where galaxies gather into strands, into sheets, into walls, forming shapes that resemble a colossal cosmic foam. Each strand in the cosmic web is a place where galaxies line up into long, slender chains, stretching tens or even hundreds of millions of light years. These strands aren't rigid structures. They are more like streams of matter drawn into thin, glowing threads, regions just slightly denser than the space around them. These threads, called filaments, link galaxy clusters together. At the intersections where many filaments meet lie nodes, galaxy clusters where hundreds or even thousands of galaxies are pulled together by gravity, creating enormous superclusters. These structures reveal that the universe was never shaped by randomness. It has form, organization, and sweeping contours carved by the long interplay of matter and gravity. Between the filaments and superclusters lie the voids, vast chambers so immense it is difficult to imagine their scale. These voids span tens, even hundreds of millions of light years, while containing only a sparse handful of galaxies. They are like empty bubbles resting between the luminous strands of the web. Seen from far enough away, the universe resembles a foam, bright threads woven into a skeletal framework, with each cell holding a deep, quiet darkness. If the cosmos could be shrunk to the size of an object held in your hands, it might look like a delicate sponge, with light marking the connecting strands and shadow filling the hollow spaces. This web is not something imagined or exaggerated. It has been observed through massive astronomical surveys like the Sloan Digital Sky Survey, which mapped millions of galaxies in 3 dimensions. When the data are stitched together, the long filaments and broad sheets emerge like a sprawling labyrinth stretching across the universe. The astonishing thing is that these structures are not only beautiful, but deeply meaningful. They are the surviving imprints of the earliest ripples in the cosmic plasma, magnified by expansion and shaped over time by dark matter. The largest structures we see today began as tiny waves in the newborn universe, much like small ripples on the ocean that, gathering over long distances, can sculpt entire patterns across the sea. Moving through this cosmic web in the imagination feels like drifting among towering columns of light, each one a stream of billions of stars. These strands weave together into shapes that feel soft and organic, without sharp edges, like the glowing threads of some vast cosmic organism. And between them, the voids, quiet, enormous, create a kind of poetic contrast. Not every region of the universe is dense and vibrant. Some are almost empty, places so still that only a lone, distant galaxy sends out a faint glimmer. It is this rhythm between fullness and emptiness that gives the universe its unique character on the largest scales. Beyond their visual beauty, the filaments reveal something profound. The universe has no center, no privileged point, no special direction. Everywhere, when observed at a grand enough scale, displays the same pattern. This reinforces one of cosmology's fundamental principles, that the universe is homogeneous and isotropic on large scales. The web stretches out in every direction, without beginning or end. It does not favor one region over another. It is simply the natural consequence of physical laws unfolding over 13.8 billion years, a map drawn by gravity and dark energy. To see this web clearly, humanity had to gather light from millions of distant sources. Yet what makes it poetic is the feeling that even though we are such a tiny part of this immense structure, we can still perceive its entire shape. It is like a quiet reminder that the universe is held together by invisible connections, and that every bright region and every dark one plays a role in the whole. Draped over the ancient glow of the CMB, the cosmic web becomes the next chapter in the story of how space formed and evolved. The existence of the cosmic web shows that even across scales too vast to grasp, the universe follows a natural order, an organization that is not random or directionless. And from this understanding, the mind drifts toward the next question. If the cosmic web has brilliant filaments and enormous empty regions, then what exactly are those empty regions? Why are they so large that they defy intuition? Do they hold something special, or are they simply the spaces between the rivers of galaxies? Those questions gently guide the journey forward, toward the next landscape, where the cosmic voids begin to emerge like dark hollows in a shimmering lattice. Each void carrying its own quiet story of stillness in a vast and ancient universe. As the image of the cosmic web rises like an immense foam filled with glowing strands, the mind naturally drifts toward the dark spaces woven between those threads. If the filaments are where galaxies gather, then the spaces inside them open up like the empty rooms of the universe, vast, quiet, and nearly devoid of anything at all. From that contrast, the journey eases into another layer of structure, where absence becomes the central presence, where emptiness carries its own strange, contemplative beauty. These are the cosmic voids, regions so large they stretch the limits of imagination, yet almost mysteriously empty. A void is not a rip in the fabric of the universe, not a place where space has torn or disappeared, and not a doorway out of the cosmos, as some might assume. A void is simply a region with an extremely low density of matter, a place where galaxies are unusually scarce. In a universe where galaxies can appear nearly everywhere, from bright clusters to dense strands, voids are the silent regions, so vast that light seems to travel through an ocean of cold night before encountering a single lonely galaxy. One of the most famous voids is the Boötes Void, a colossal expanse that makes anyone who hears about it pause for a moment. The Boötes Void spans about 330 million light-years, a scale almost impossible to express in words, considering that our own Milky Way, is only about 100,000 light-years in diameter. And yet, within this enormous stretch of space, instead of the thousands of galaxies one might expect, astronomers found only about 60. That number is so small that the void appears like a cosmic desert, where faint lights drift sparsely through endless darkness. Stepping into the Boötes Void in the imagination is like entering a cold, soundless desert. If the cosmic web resembles the glowing cities of galaxies, then a void is like a wide, untouched valley where nothing has stirred for ages. Each empty region carries a quiet beauty, not from light, but from the lack of it. Inside a void, the eyes are no longer distracted by billions of stars. They float freely in a space so vast that even loneliness feels peaceful. These dark expanses are not signs of endings, but proof of the universe's natural balance in the distribution of matter. It is important to understand that a void is not outside the universe. There are no holes leading out of space, no boundaries opening into nothingness. Voids exist entirely within the cosmos, nestled among its filaments and clusters. They are a natural part of the structure of space, born from tiny differences in density during the universe's earliest moments. Regions that began slightly less dense became emptier over time, as surrounding matter was pulled toward the denser areas, where filaments and galaxy clusters formed. Gravity carved out these hollow regions, shaping vast pockets of space on the cosmic map. Voids are not just empty spaces, they have distinct characteristics. Temperatures inside them tend to be lower, and fluctuations in the cosmic microwave background are gentler. Light from galaxies outside a void often stretches and dims as it travels through, growing even fainter. Within voids, space may expand slightly faster than average, because there is so little matter to slow that expansion. This makes voids like special pockets of space, where the universe flows at its own quiet pace. From a more delicate perspective, voids reflect the universe's grand contrast. The cosmos needs both densely packed regions and open, empty ones to form its full picture. If every place were crowded with galaxies, large-scale structures would lose their definition. If every place were empty, the universe would lack the beauty of woven light. A void is like the stillness between musical phrases in a galactic symphony, not forgotten, but forming the gentle backdrop that brings harmony to the luminous design. What's fascinating is that even in these empty realms, galaxies do exist, few, isolated, and special. The galaxies found within voids are called lonely galaxies, small worlds spinning quietly in the deep dark. They are like solitary sparks in a cosmic desert, living more slowly, more peacefully, sometimes with structures unlike those in crowded filaments. Free from constant interactions, collisions, or dense environmental pressures, they evolve at their own pace, writing rare stories of existence shaped by silence. A place like the Boötes Void often evokes the feeling of standing in a dark night, where every sound is swallowed by shadow. Yet this emptiness does not feel unsettling. Instead, it carries the spaciousness of a universe that breathes, reminding us that cosmic structure is not rigid, that there are always spaces to rest, to pause. A void becomes part of the universe's rhythm, a place where space continues to stretch, unburdened by the weight of galaxies. Emphasizing that voids are not exits from the universe brings reassurance. Despite their emptiness, they are still part of the same cosmos as any bright cluster or glowing filament. Space keeps expanding smoothly. There are no tears to fall through. A void is simply a region where matter is too scarce to form radiant structures, It does not mark any boundary except that of its own quiet nature. When we imagine voids as the universe's deep breaths, the mind gently shifts to the next question. If these empty regions can spread across hundreds of millions of light years, then how large are the biggest structures spanning the cosmos? Is there a limit to the walls of galaxies, the superclusters, the immense bridges connecting the filaments? And when observed from a sufficiently grand scale, does the universe still look like a web? Or does it soften into a smooth, uniform tapestry? From this profound emptiness, the journey moves forward to the next chapter, where the universe's largest structures fade gently into its sweeping uniformity, like a transition from intricate detail to a distant, tranquil panorama. As the colossal voids appear like deep pauses within the symphony of the universe, the mind gently expands beyond each empty region and each individual filament. From an even more distant vantage point, a soft question emerges. If the universe contains vast emptiness like the Boötes Void, and also threads of galaxies stretching hundreds of millions of light years, then how large can the biggest structures ever observed truly become? Is there a natural limit to the size of cosmic structures? Or can space gather galaxies into shapes even larger, beyond anything our familiar sense of scale can grasp? From this desire to step back farther, the idea of the universe's largest structures and its overall uniformity begins to unfold like a panoramic scene. When astronomers first mapped millions of galaxies in 3 dimensions, they discovered that the cosmic web did not end with filaments or voids. On those maps, immense structures appeared, so enormous they left scientists momentarily stunned. Walls of galaxies stretching billions of light years, superclusters linking dozens of other superclusters. One of the most famous is the Great Wall, a gigantic galactic wall found in the late 20th century. The Great Wall spans hundreds of millions of light years, and afterward, even larger structures were discovered. The Sloan Great Wall, the Hercules Corona Borealis Great Wall, each one so immense it challenged our understanding of how the universe forms. The mere existence of a galactic wall, billions of light years long, is enough to unsteady human intuition about size. These structures aren't continuous shells of matter, but regions of higher density held together by gravity. They are evidence that the cosmos is not arranged randomly. Tiny fluctuations in early matter density were gradually amplified over billions of years, pulling material into large regions, while sparser ones grew emptier. In this way, the universe's largest structures formed within a cosmos shaped by expansion and gentle, long-lasting gravitational flow. Yet even though these structures are nearly unbelievable in scale, they still do not violate a key principle. When viewed at a sufficiently large scale, the universe becomes uniform. This sounds paradoxical. How can the universe be uniform if it contains structures billions of light years wide? But uniformity does not mean identical everywhere. It means that, on average, across great distances, the number of galaxies, the density of matter, and the types of structures become similar in every direction. If we extend our view beyond the filaments, beyond the voids, beyond even the largest superclusters, the local differences begin to fade. The universe starts to resemble a pattern repeating across space, without a center, without an edge, and without a preferred direction. No matter where we look, the distribution of matter gives a similar impression. This is what makes the universe such a remarkable place. Unlike a city with a center or a building with a clear structure, the cosmos has no origin point. There is no chosen center. There is no edge marking its end. No direction holds special meaning. Every point in the universe can consider itself the center of the observable cosmos from that location. And each observer's cosmic bubble would be the same size as ours, if they existed. There is something strangely comforting in this. Nowhere in the universe is more special than anywhere else when viewed at a grand enough scale. Any observer in any galaxy would see the universe stretching out in a similar way overall. From any vantage point, the view would create an observable bubble about 46.5 billion light-years in radius. Not because the observer is truly at the center, but because that distance marks how far light has traveled since the universe began, measured from their position. From this understanding, we see that even though enormous structures can appear locally, they do not break the universe's broader uniformity. The cosmos is like a mosaic. Up close, each piece is distinct. From far away, the whole becomes balanced and even. A galaxy far away may differ from the one near us, but the average distribution across billions of galaxies remains astonishingly harmonious. This uniformity carries another quiet message. The universe has no physical boundary. There is no place marking the end of structure, even when we encounter immense voids or galaxy walls. These structures are not limits. They are simply features, parts of a web that extends endlessly or nearly endlessly. From a greater distance, the repetition of these structures makes the universe feel like a vast musical composition, unfolding with a familiar motif. Filaments here, voids there, dense clusters, sparse regions. And no matter how far we travel, the motif continues, softly repeating, gently flowing. There is no wall to stop it, no region where light fails, no point where matter simply vanishes. This idea, once it settles into thought, brings a strange peace. We realize that the universe is not built from boundaries. It has no edge to touch, no final line, only the expansion and repetition of its structures, as if space is weaving itself into an endless tapestry. And from this understanding, the mind begins to drift toward a brighter, deeper question. If the universe has no structural edge, what happens if we follow the trail of time instead? Does the boundary of space connect to the boundary of time? And when we move backward into the past, what lies beyond the largest structures once we reach them? That soft question carries the journey into the next chapter, where time becomes the center of thought, and the Big Bang rises like the opening moment of a story, not just about space, but about the origin of everything. As the image of the universe's uniformity becomes clearer, the mind gently shifts from space into an entirely different dimension, the dimension of time. The largest structures in the cosmos, even those spanning billions of light years, are still only patterns woven onto the tapestry of space. Yet that tapestry has a single thread where it all began, a starting point to which all existence returns when we shrink the picture down far enough. If space has no physical edge, time seems to hold a sharp beginning. The Big Bang, the moment in which the ideas of before and after first became meaningful. This notion doesn't appear like an abrupt cut. It forms naturally as we realize that the vast structures, superclusters, filaments, enormous voids, are all the outcome of a long evolutionary process that traces back to a very particular point. When we follow the formation of these structures back through time, we eventually reach an era when space hadn't yet stretched to its current size. And from that point, a quiet question arises. Was there a first moment when the universe emerged from an extremely hot, dense state and began expanding into the grand shapes we observe today? Science names that moment the Big Bang. Despite the explosive sound of its name, It bears no resemblance to the kinds of explosions we encounter in daily life. There was no central blast, no surrounding environment being pushed outward. Instead, space itself expanded. Time began to flow. Energy, matter, gravity, and every physical law were shaped from that instant. The Big Bang wasn't an explosion in space. It was the appearance of space and time themselves. According to our best observations, this event took place about 13.8 billion years ago. Its echoes still remain in the cosmic microwave background, in the abundance of light elements, in the accelerating expansion of galaxies, and in the patterns of matter distribution we've mapped. These signatures are like lingering memories, confirming that the universe was once smaller, denser, and unimaginably hotter than it is today. But as we trace our way back to that moment, a gentle question rises. What came before the Big Bang? It is a question both simple and deep, like asking about the origin of a road that created the space for the road to exist. In traditional physics, the answer is that time began with the Big Bang, and so the question of before may not make sense in the usual way. If time is a dimension of the universe, then before the Big Bang is not a moment, but the absence of moments altogether. And yet science does not stop at this humble answer. Even while acknowledging we lack certainty, physicists have crafted subtle hypotheses to describe what may have existed before everything began. These models are not finished paintings, more like gentle sketches that invite human imagination to step one layer deeper into the hazy boundary of understanding. One such idea is cosmic inflation. It describes a phase of ultra-rapid expansion that happened immediately after the universe's birth. If inflation can happen once, could it happen many times in different regions of space? This leads to the concept of a multiverse, where our universe is just one bubble in a vast sea of countless others. In this view, the before of our Big Bang might be another inflationary phase, or a different universe altogether that created the conditions for ours to form. Another, more delicate idea is that of a cyclic universe. In this scenario, the cosmos may undergo endless cycles: expansion, slowing, contraction, and rebirth into another Big Bang. In such a model, our Big Bang is not the absolute beginning, but a transition, the turn of a cosmic breath. Each cycle opens a new universe, suggesting that the before might have been an older universe collapsing into its final moment. Yet another hypothesis comes from loop quantum gravity, which proposes that on the tiniest scales, space is not smooth but granular, woven from tiny loops. In this approach, the Big Bang's singularity may not exist at all. Instead, a prior universe could have shrunk to its smallest possible size before bouncing outward again, like a spring compressed to its limit and then released. These ideas are not meant to deliver final answers. They act more like gently opened doors, letting us sense that there may be something beyond the boundary of time, something not yet clear, but perhaps not empty either. They remind us that while the Big Bang marks the beginning of time in the standard model, it may not be the beginning of all reality. What's fascinating is that when we speak of the boundary of time, human thought becomes softer. Gone are the straight lines of cosmic structure, the galaxy walls, the filaments of light. What remains are layers of time as thin as mist, fading toward a point where all physical laws dissolve into a unified state. The feeling is gentle, like approaching the floor of a deep well, where light cannot reveal the shape, yet still leaves a quiet echo. When we ask, what came before the Big Bang? We are not only asking about physics, we are asking about the limits of understanding, about the reach of a small species trying to comprehend an enormous universe. And in facing this question, we glimpse the beauty of the scientific journey. Not the pursuit of absolute certainty, but the willingness to step into the unknown with a kind and curious mind. From this boundary of time, the journey does not stop. If we can imagine what might have preceded the Big Bang, then what follows it, through the universe's 13.8 billion year evolution? Could cyclical models point toward another Big Bang in the future? And if the Big Bang is the earliest event we can observe, what theories might extend beyond it, forming a larger story of existence? These questions softly guide the mind into the next chapter, where the cyclic universe enters like a deep, resonant note in the symphony of time, opening the possibility that the beginning may be only one chapter in a story that never truly ends. As the mind glides softly across the boundary of time surrounding the Big Bang, a strange feeling emerges. The sense that this beginning, though monumental enough to shape the entire history of the universe, might not be the very first beginning of all things. The Big Bang appears as the opening chapter we know, but could it actually be a middle chapter of a far larger story, stretching across cycles humanity has glimpsed only briefly, like a small slice of an endless chronicle? From this thought, the journey naturally shifts to an idea found in ancient civilizations and revisited by modern science in a completely different language. The cyclic universe, a cosmos that is not born just once, but undergoes endless cycles of creation and rebirth. The cyclic universe hypothesis does not reject the Big Bang. It accepts it as a real event, while opening the possibility that the Big Bang may be one of countless moments when space and time are renewed. In this view, the universe is a vast loop in which expansion and contraction alternate across spans of time too immense to fathom. Each cycle is a universe, with its own structures, its own history, its own fate. One prominent model is the Big Crunch Big Bounce scenario. According to it, the universe does not expand forever. One day, in an unimaginably distant future, gravity might overcome expansion, causing the universe to slow down and begin contracting. Galaxies would drift closer together, the distances between cosmic structures would shrink, and temperatures would rise. Space itself would no longer widen, it would tighten. Eventually, all matter and energy would compress into a state as hot and dense as the one before the Big Bang. But instead of ending there, the universe might rebound in an event called the Big Bounce. That rebound could be the next Big Bang, giving birth to a new universe. This image resembles a cosmic breath, inhaling, exhaling, contracting, expanding, ending one cycle only to begin the next. If our current Big Bang is just one step in such a sequence, then the question, what came before the Big Bang, may have a simple answer. Before our Big Bang was the universe that came before it, a fully formed cosmos that evolved, contracted, and reached its smallest state before giving rise to the next. Another, more delicate model arises from string theory and brain cosmology. In this picture, our universe may be a three-dimensional brain floating within a higher dimensional space. If two such brains collide, the energy released could trigger an event akin to the Big Bang. This means the Big Bang was not the creation of all space and time, but rather the result of a collision between brains in a larger dimensional setting. And if these brains drift and oscillate, they might collide repeatedly, creating many Big Bangs over the long history of the multidimensional cosmos. This opens a fascinating possibility. Cosmic cycles need not be contractions and bounces. They might be periodic collisions between parallel worlds. With each collision, the compressed energy forms a new universe, one whose physical laws and structures could be similar or slightly different. These cycles might span trillions of years, far beyond anything the human mind is accustomed to imagining. No matter the model, the cyclic universe brings a particular feeling, the sense that an ending is not truly an end, and a beginning is not the absolute beginning. Space and time may be a continuous flow in which every ending quietly opens the door to another beginning. This makes the Big Bang both extraordinary and ordinary. Extraordinary because it gave birth to our world, and ordinary because it may be just one of many such events across cosmic time. The image of the universe reborn like a phoenix rising from its own ashes is often used to describe this model. Not because science borrows from mythology, but because it is one of the most beautiful ways to express the gentle repetition of the cosmos. Dying only to live again in a new form, evolving across an endless expanse of time. Each Big Bang is a moment when the universe opens its eyes, and each big crunch is a moment when it closes them, preparing for another awakening. But it is important to recognize that all of this remains hypothetical, constructed from mathematics and theoretical physics. There is no direct evidence that the universe truly cycles, yet the idea provides a profound and evocative glimpse of what might lie beyond our Big Bang. Not a distant region of space, but a different universe that once existed before ours. And if this is true, then our Big Bang is not the first moment of reality, but simply the nearest milestone in an endless chain. As the mind drifts across this idea, a gentle feeling spreads, like the universe no longer appears as a straight line with a first point, but as a vast circle with no beginning or end. In that circle, time flows with the rhythm of long cycles, each contraction and expansion offering a new rebirth. And if this is the case, the question of the universe's ultimate origin becomes unanswerable in the same way that one cannot name the first point on a perfect circle. From the idea of a cyclic universe, the journey opens toward an even bolder possibility. If countless Big Bangs might follow one another within the same cycle, could there also be countless universes existing in parallel, each with its own Big Bang, even if they do not belong to the same sequence? That thought leads us to the threshold of the next chapter. The multiverse, a perspective that expands the imagination far beyond the edges of our own cosmic horizon. As the idea of a cyclic universe spreads gently through thought, the sense of standing before an endless circle of creation and dissolution becomes more vivid. Each cycle of Big Bang and Big Crunch feels like a book without a first or last page, only chapters continuing one after another. But just as that circle becomes complete in the imagination, another doorway opens. A doorway that suggests not only that the universe may repeat in cycles, but also that our Big Bang might not be alone in this rhythm of rebirth. Instead, it may be just one among countless beginnings, not only occurring sequentially through time, but happening simultaneously in separate regions of space. From the rhythm of cycles, the mind softly opens into a far grander idea: the multiverse, the possibility that reality is not singular, but may stretch across countless variations. If the cyclic universe resembles a steady, gentle flow, then the multiverse opens up like a vast ocean where each universe is just a small ripple on its surface. In this view, the Big Bang is not the singular event that brought all reality into existence, but simply one bubble forming within a larger field of expansion. And within that ocean, other bubbles may be forming, expanding, evolving, and fading, completely separate from the bubble in which we live. One of the strongest theories supporting this idea is eternal inflation. Inflation was originally introduced to explain why our universe appears so smooth and flat. It describes a brief period of ultra-rapid expansion right after the Big Bang, during which space multiplied exponentially. But when inflation is extended into eternal inflation, space doesn't expand once and then stop. It expands forever at the foundation of reality. In this ever-growing sea of space, certain special regions cool and stabilize enough to end their inflation and create a localized Big Bang, like bubbles forming in boiling water. Each such bubble may become a universe of its own. Ours is just one among them. Each bubble could emerge with different conditions, different energy densities, different expansion rates, even different physical laws. Some bubbles might expand too quickly to form galaxies. Some might expand slowly and allow stars to take shape. Some universes might have stronger or weaker gravity. Some might lack dark matter. Some might have physical constants shifted by the tiniest amount, enough to change everything. This idea paints a gentle picture. At the edge of the observable universe, there may not be an endless void, not a wall, not a drop-off into nothingness. Instead, there may be other universes quietly existing beyond our reach, like faint glimmers in a night sky far larger than the sky our eyes can see. Each universe is a flicker of light in a cosmic night beyond ours. Not the night of a single universe, but of the entire multiverse. Some models even suggest that these bubble universes might interact. If two cosmic bubbles collide while expanding, their contact might leave imprints on the cosmic microwave background, like the ripples formed when two droplets touch. Some scientists have searched for circular patterns in the CMB map that might be remnants of such collisions. The results remain uncertain, yet the idea evokes the sense that our universe might not be isolated. It might have neighbors, even if they are separated from us by unreachable distances. In another version of the multiverse, emerging from string theory and its landscape of energy configurations, a universe may exist as one possibility among an enormous number of potential energy states. Each state corresponds to a universe with its own set of physical constants. This landscape might be unimaginably vast, with the number of viable universes estimated at around 10^500, so enormous it escapes human comprehension. Though the models vary, they all suggest something profound. Our universe may not be unique. There might not be a single ultimate cosmos containing everything. Instead, there may be an immense collection of universes, each born from its own Big Bang, each with its own history and structure. In this ocean, we are merely one drop, existing quietly in our space, unaware of the other drops drifting beyond reach. Of course, all of this remains hypothetical. No current instrument can directly observe other universes, if they exist. No signal crosses the boundary between cosmic bubbles to announce their presence. But this does not dim the appeal of the idea. The multiverse is not just an explanation for our origins. It is a reminder that reality may be far more expansive than anything we can see, measure, or imagine. This idea carries a peaceful feeling. No matter how small we may be within our universe, we are still part of something larger, something so vast it defies all naming. And if other bubble universes truly exist, then the question, what lies beyond the edge of the universe, might be answered with the image of a greater space holding countless universes, each one a separate story, a separate chapter, a separate melody. As this thought settles, the journey drifts gently toward the next question. If countless parallel universes might exist, does time unfold the same way in each one? Where is our universe headed? And what might be the ultimate fate of all these universes together? From the idea of the multiverse, the thread of thought moves gradually into the far future, where space keeps expanding and our universe enters its final chapters. As the idea of the multiverse slowly settles, a feeling spreads like standing before an endless ocean of possibilities. If our Big Bang is only one bubble in a sea of other universes, then our existence becomes a small story, but not a lonely one, in a reality so vast it resists comprehension. And from looking outward into other bubbles and parallel realities, the mind gradually returns to the universe we know. Not to narrow its vision, but to ask a question every civilization eventually wonders about. With everything it contains, where is our universe going? From reflections about origins and structure, the journey softens into the far future, a place where time stretches beyond every familiar measure, where galaxies and stars follow destinies that cannot be avoided. And here, a new chapter opens with the realization that, just as every story has a beginning, the universe too is moving towards something, whether a conclusion or an endless state. The future of the universe is not only a story about stars and galaxies, but a story about expansion rate and about dark energy, that mysterious component making up roughly 68% of the universe's total energy. Dark energy does not shine, does not interact strongly, does not leave obvious traces, yet it carries one strange property. It pushes space to expand faster over time. And this acceleration opens multiple possibilities for the universe's long-term fate. Looking at the present, we see galaxies slowly drifting apart. Their light stretches as space expands, becoming redder, fainter, and eventually disappearing from view. In billions of years, distant galaxies will slip beyond our cosmic horizon, like tiny sparks sinking into an endless night. Their retreat is not caused by motion through space, but by the expansion of space itself. The galaxies aren't running away. The fabric beneath them is stretching. It feels like watching boats drift apart on a sea that expands in every direction. No one rows the boats. The water pulls them away. The universe is doing the same to galaxies, and as we look toward the future, we realize that this accelerating expansion will shape the rest of cosmic history. From here, imagination opens a door into a far-off future. A time when the night sky grows dimmer, not because stars have burned out, but because the universe beyond our local group will no longer be visible. Galaxies outside our gravitationally bound neighborhood will vanish from sight, leaving only a handful of galaxies trapped together by gravity. If a civilization exists then, they will gaze at their sky with no way of knowing that the universe was once so vast. The entire expansion history we observe today will be lost to them forever. But what lies even farther ahead? What unfolds after 1014, 1020, or even 1040 years? Our imagination must stretch beyond its usual limits to keep pace with such timelines. In the early stages of the distant future, stars will continue evolving along their natural paths. Massive stars will die first, collapsing into neutron stars or black holes. Small stars, the red dwarfs, will live the longest, shining gently for trillions of years in a universe that grows darker and wider. But even the most enduring stars will eventually run out of fuel. When that happens, the universe will enter what cosmologists call the era of stellar remnants, where light becomes as rare as a precious gem. In that era, the night sky will no longer hold glowing arcs like the Milky Way. Instead, it will be lit only by the faint glimmer of lonely red dwarfs, quiet black holes, and cold wandering planets with no home. Every star, bright or weak, will ultimately reach the same destination: extinguishment. But extinguishment is not disappearance. They leave behind resilient remnants scattered across space like embers of an immense cosmic fireplace. Yet the universe's fate is shaped by more than the destinies of stars. It depends on the future behavior of space itself. As dark energy continues accelerating the expansion, the galaxies we see today will fade into a permanent darkness. Space will grow so vast that all paths of light will be severed. From the perspective of the far future, the universe will become a silent expanse where isolated galaxies drift through an ocean of night with no boundaries. And this is only the broad outline. In the trillions upon trillions of years to come, large-scale structures will dissolve, black holes will swallow what remains, and they themselves will slowly evaporate through Hawking radiation. This evaporation is unimaginably slow. It may take up to 10 out of 100 years or more. But given enough time, even the mightiest black holes cannot resist this steady fading. One day, in an immeasurable future, the universe will enter a state cosmologists call the final cooling, where temperatures fall close to absolute zero, where no energy differences remain to sustain physical or biological activity. A still, dark night, not because light is absent, but because all sources of light have ended. But this vision is not meant to inspire gloom. It is merely a chapter in a larger story science is trying to understand. And within that stillness lies a special kind of beauty. The beauty of infinite time, of processes unfolding slower than anything in human history, of a universe so vast that every ending arrives gently, without noise. As the mind sinks into this picture of the future, another question emerges. If the universe expands forever and approaches this cold end, is that the only possible fate? Or are there other scenarios, stranger, more powerful, that could shape the universe's final destiny? From the soft image of a distant future, the journey opens into the next chapter, where heat death, the Big Rip, and other possibilities appear like different pathways in the long story of time. As the picture of the far future unfolds, galaxies fading into the darkness of an ever-expanding cosmos, the mind naturally turns toward a deeper question. If the universe continues to expand forever, what happens at the very end of time? The vision of galaxies drifting out of sight, of stars dimming, of space filling with darkness is only the opening chapter of a much longer story. And from this quiet, growing image, the journey moves softly toward one of the most widely considered possibilities for the universe's final fate: heat death, a scenario in which the cosmos approaches a state of complete thermodynamic stillness. The idea of heat death arises from the realization that the universe is not only expanding, but becoming more and more evenly distributed in energy. In everyday life, we watch warm objects lose heat to their surroundings until they reach equilibrium. The universe is similar, though on a scale far beyond comparison. As energy spreads throughout the stretching fabric of space, the differences in energy, differences that power motion, structure, and life, grow weaker. In the heat-death scenario, dark energy behaves like a constant embedded in space itself. It continues to drive eternal expansion, but not in a violent way that tears structures apart. Rather in a steady, persistent, irresistible rhythm. This expansion stretches the cosmic fabric thinner and thinner, causing galaxies to drift so far apart that they will eventually stop interacting entirely. At the moment, stars still burn brightly. Nuclear fusion within their cores continues to create light and heat, sustaining their long, delicate dance of energy. But that fuel is not infinite. In tens to hundreds of billions of years, massive stars will burn out first, leaving behind compact remnants. Neutron stars, black holes, and especially the dim leftovers of small stars, white dwarfs. These white dwarfs will cool slowly, eventually becoming black dwarfs. Cold, dark objects that emit almost no light. By then, the universe will no longer host the brilliant theaters of starlight we see today. As the formation of new stars declines and ultimately stops, the production of concentrated energy and light will also end. Galaxies will transform into collections of stellar remnants, rotating slowly within a space that grows darker with every passing epoch. The last stars will be like faint embers in a cooling furnace, fragile, barely glowing, almost indistinguishable from the dark around them. Then begins an era so long that time itself becomes difficult to hold in the mind. The age of black holes. Black holes will be the last major structures that retain their form. In an aging universe, these deep wells of gravity become the final shelters for matter. Whatever random collisions still occur will be swallowed, allowing black holes to grow slowly. But even they, with all their power, are not eternal. Through Hawking radiation, black holes gradually evaporate. This process unfolds with astonishing slowness, taking roughly 1060 to 10100 years, depending on size, for a single black hole to vanish completely. Near the end of its life, the black hole shrinks, its radiation strengthens, and then it dissolves into space as a brief flash of light. Not an explosion, but a quiet final sigh of energy fading into the expanding void. After this comes the last era, the age of perfect stillness, where no stars remain, no galaxies remain, no black holes remain. Only scattered subatomic particles drift within a cosmos whose temperature hovers infinitesimally above absolute zero. In this environment, no temperature differences remain to support physical or biological activity. No energy gradients exist to drive meaningful motion. All macroscopic physical processes come to a halt. This is the thermodynamic end of the universe, a state known as maximum entropy. Not a collapse, not an explosion, just a long, soft fading of all activity. Like a piece of music ending with a final note that stretches into silence. In that silence, nothing new happens. No meaningful change remains. No interactions are strong enough to produce the kinds of phenomena we know. This description may sound somber, but it carries a strange serenity. It is not a sudden or violent ending. It is a process so long that the entire history of humanity, of Earth, of the galaxies themselves becomes a collection of tiny, fleeting moments in comparison. And this makes heat death feel like a distant story, one beyond direct human imagination. In this vision, space does not become dangerous or frightening. It becomes calm. Its quietness comes not from loss, but from perfect balance. No place is hotter or colder than another. No direction means more than any other. Everything melts into a uniform ocean of dispersed energy. And in that sameness, the universe reaches its final state, the complete stillness of thermodynamics. Heat death is not annihilation. It is the cessation of complexity. And from this angle, it resembles an endless night, one where motion gradually dissolves, leaving only the softness of a universe cooled to stillness. From this vision, the next natural question appears. Is heat death the only possible ending? Or could dark energy behave in a more extreme way, driving the universe toward a completely different fate? That thought becomes the bridge to the next chapter, where a far more dramatic future is imagined. The Big Rip, a scenario in which space itself may be torn apart by its own accelerating expansion. As the vision of heat death settles, a universe sinking into infinite stillness, the mind might easily assume that this is the gentlest, slowest ending the cosmos could ever reach. A conclusion without explosion or violence, simply a quiet fading into cold uniformity. But from within that calm, another path emerges, a path in complete contrast, where the universe does not dim slowly but ends in a single catastrophic cosmic tearing. And from that vantage point, the story drifts gently into one of the most dramatic yet distant scenarios imagined for the universe's fate: the Big Rip. If heat death rests on the idea that dark energy remains constant through time, the Big Rip is built on a different hypothesis: that dark energy does not stay fixed. It changes, and not only changes, but grows stronger over time. This kind of dark energy is sometimes called phantom energy, not because it is supernatural, but because its properties stretch beyond familiar physics. As dark energy intensifies, cosmic expansion not only continues, but accelerates. A little faster at first, then faster still, eventually reaching an almost dizzying pace. And if this acceleration becomes strong enough, every structure in the universe must confront expanding forces that exceed all other forces: gravity, electromagnetism, even the forces binding matter itself. The journey toward the Big Rip begins gently. In the next tens of billions of years, space expands faster and faster. Galaxies beyond the local group drift away so rapidly that their light can no longer outrun the expansion to reach us. Those galaxies fall beyond the cosmic horizon, as if drifting into a distant fog where they can no longer be sensed at all. The night sky grows emptier, not because light fades as in heat death, but because space expands so quickly that all light is stretched into invisibility. But this is only the beginning. As dark energy strengthens further, it begins to tear apart larger structures. First come the superclusters, massive formations bound by gravity. In the Big Rip scenario, gravity is no longer strong enough to hold them together. They gradually disperse, drifting away piece by piece. Galaxies that spent billions of years as cosmic neighbors are carried apart into widening emptiness. Next comes the galaxies themselves. The Milky Way, which holds our solar system, is held together by the gravitational web binding hundreds of billions of stars. But in the Big Rip, even that binding is overcome. Stars begin to drift apart, each one pulled from its orbit. The galaxy unravels like mist caught in a rising wind. Then the process moves inward to smaller scales. The solar system can no longer remain intact. The expanding force overcomes the gravity holding Earth to the Sun. One by one, the planets drift from their orbits, not because they choose to wander, but because the space between them grows faster than gravity can restrain. Although it sounds dramatic, this unraveling is not sudden. It follows a clear sequence, from the largest structures to galaxies, down to individual star systems. Yet the Big Rip does not stop there. As dark energy continues intensifying, it eventually reaches a point where even atoms, held by the powerful electromagnetic force, can no longer resist. In the final moments, protons, electrons, and neutrons are torn apart. No molecules, no atoms, no nuclei. The universe dissolves into its smallest components, like a building pulled apart brick by brick until nothing remains but dust. This moment marks the end of the Big Rip, a cosmic rupture in which everything, from galaxies to the tiniest particles, is torn apart by runaway expansion. There is no explosion, no brilliant flash, only a total disintegration of structure. and afterward, nothing can hold together. Space continues to expand, but there is no matter left to stretch, only cold, solitary particles drifting without purpose in an endless void. It is a more violent vision than heat death, yet so distant that it remains difficult to truly imagine. If heat death is the slow dimming of a cosmic ember, the Big Rip is the dramatic tearing of the cosmic tapestry itself. Yet it must be said, this scenario depends entirely on whether dark energy grows stronger over time. Current observations suggest dark energy behaves more like a constant, making the Big Rip less likely than heat death. But science always leaves room for possibility, and the Big Rip, even as a hypothesis, helps us explore the outer limits of what the universe could do if its fundamental forces behaved differently. In the quiet of this thought, the Big Rip does not appear as a warning, but as another chapter in the universe's grand book. A scenario not meant to frighten, but to widen the imagination, showing how reality might transform when familiar laws are pushed to their limits. And from here, the mind drifts gently toward the final part, where the story gathers these possibilities together and asks, among all these paths, might there be even subtler, more unexpected futures still waiting to be discovered? As the vision of a universe stretched to the point of dissolving into its smallest particles slowly fades, the mind begins to open into another space, a space filled with possibilities not yet fully told. If heat death paints an endless stillness, and the Big Rip sketches a violent unraveling of space itself, then together they reveal something important. The future of the universe is not confined to just two paths. Between these models lie other branches, faint, suggestive possibilities, like unwritten chapters in a book we've only begun to read. And here, the journey drifts gently toward those alternative scenarios, rare, subtle, but still left open by modern physics. One of the most significant hypotheses that widens the story of the universe's fate is the Big Crunch. This scenario is the exact opposite of the Big Rip. Instead of dark energy strengthening, the Big Crunch emerges from the idea that dark energy may weaken over time, or even vanish entirely. If that happens, gravity, the force that pulls everything together, will gradually regain dominance. In this picture, the expansion of the universe slows, then halts, and eventually reverses. Space begins to contract. Galaxies draw closer, energy density rises, and the universe warms back toward the extreme temperatures of its earliest moments. In this scenario, the universe does not grow cold. It returns to a hot, dense state. And if the contraction continues, all structures, galaxies, stars, planets, are squeezed toward an incredibly small point. A point reminiscent of the beginning we call the Big Bang. Some theoretical models suggest this final point isn't an ending at all, but the prelude to a big bounce, a rebound that launches the universe outward again in a new cycle. This idea creates a different way of viewing cosmic time, not as a single line moving in one direction, but as an endless cycle. In such a cyclic model, the universe expands, then contracts, then bounces outward again, repeating through countless rounds. Each cycle may have different characteristics, different densities, different structures, different microphysics, but all exist within an infinite flow of renewal. Yet even though the Big Crunch and Big Bounce are compelling, current observations of dark energy show that the universe is accelerating, not slowing. This makes the Big Crunch unlikely, though not impossible, and still present on the map of cosmic hypotheses. Beyond the Big Crunch lies another scenario born from the quantum world: vacuum decay. This is perhaps the strangest possibility, because it isn't driven by galaxies drifting apart or space expanding. It comes from the stability of the quantum vacuum itself, the underlying energy field that permeates the universe. According to some models, the vacuum state of our universe might be a false vacuum, not perfectly stable. If so, there is a tiny, tiny chance that a bubble of true vacuum could appear somewhere in space. This bubble would expand at the speed of light, sweeping away all existing laws of physics. No structure, no atoms, no fundamental forces would survive in their familiar form. The universe as we know it would be replaced by a new state with entirely different rules. Though it sounds startling, this scenario isn't a catastrophic disaster in the usual sense. If it occurs, there will be no warning, no pain, no time to perceive it. It is simply a phase transition, like water freezing, with its molecules unaware the change is happening. And the probability of such a transition in any near future is effectively zero. It lies on timescales far beyond heat death or the Big Rip. Between these extremes are additional possibilities: slight changes in the nature of dark energy, transitions between different cosmic phases, or microphysical effects we haven't yet discovered. Some quantum cosmology models even propose that the universe has no beginning or end in the traditional sense, but is part of a much larger, timeless structure. In that structure, what we call past and future might simply be the limited viewpoint of beings living within one small slice of a broader temporal landscape. What matters in all these scenarios is this: every one of them lies in a future so distant it escapes all human intuition. Whether in tens of billions, hundreds of billions, or even 100 years, these possibilities are not meant to provoke fear. They invite humility, an awareness of how small humanity is compared to the scale of cosmic time. At this point, the journey through the universe's possible endings feels like reading a long, multi-volume work of speculative fiction. We are living on a single page, near the beginning of the story. The chapters ahead, the ones about expansion, contraction, black hole evaporation, vacuum transitions, remain unfinished. No one knows which chapter will unfold, which will remain only theoretical, or which lies forever beyond the reach of scientific thought. And from that vastness of the unknown, Part 17 closes with a gentle feeling. Humanity does not possess the complete answer, but we do possess imagination, curiosity, and the ability to build models that help us understand our place in the cosmos. As these reflections settle, the journey moves softly toward the final part, where the entire voyage is gathered into a tender conclusion, like a wish for deep sleep under a sky full of stars. As the far-off scenarios of the universe's future gradually close, from the Big Crunch to vacuum decay, a soft feeling spreads like a thin layer of mist. These possibilities, though varied, all reveal that the universe's future stretches far beyond anything human imagination can fully embrace. And from these reflections on possible endings, the journey now drifts back, like water returning to its source, gathering every idea we explored into one unified picture. From the vast emptiness of space to the earliest moments of time, from the limits of observation to the open questions of fate, everything comes together into a single story we've traveled through side by side. The journey began with a simple question, one asked across generations. What lies beyond the edge of the universe? That question wasn't a lone punctuation mark. It was a doorway into an entire universe of thought. From the moment it opened, we moved through layered ideas stacked upon one another, from observational limits to the nature of space itself, from the oldest light to the largest structures ever known. Each layer was like a door leading to a deeper level of human understanding. We began by exploring the observable universe, the region where light has had enough time to reach our eyes after 13.8 billion years. Though only a small part of the whole, it is the region science can describe. But that boundary isn't a wall. It is a cosmic horizon, a limit shaped by the speed of light and the ongoing expansion of space. An invisible wall, not to confine us, but to remind us how much remains out of reach. From that horizon, our gaze shifted to the cosmic microwave background, the faint glow left from the universe's early youth. The CMB is not only the oldest light we can see, but a witness to the moment when the universe cooled enough for light to travel freely. And yet, the CMB is also another boundary. Behind it lies a time when light could not escape, forcing us to rely on other messengers like gravitational waves or ancient neutrinos. Leaving those limits behind, the journey moved into the realm of large-scale structure, where galaxies are not isolated islands, but threads woven into a majestic cosmic web. Filaments stretching hundreds of millions of light-years, galaxy clusters linked into vast chains, immense voids like the Boötes Void. Together, they form the largest shapes the universe has ever revealed. These voids are not holes leading outside the universe. They are simply evidence of uneven matter distribution, even though, on a large enough scale, the universe becomes astonishingly uniform. The journey then carried us from space into time. If space has a horizon of observation, time has its own boundary as well, the beginning marked by the Big Bang. Yet the question, what happened before the Big Bang, opened the door to subtle theories, cyclic universes, cosmic rebounds, or entire sets of parallel universes within a multiverse. Each idea flowed like a small stream into the vast ocean of human thought, reminding us that the universe's origin remains wrapped in the mist of the unknown. From the beginning, we moved toward the end, toward scenarios that touch the farthest limits of cosmic time. We explored heat death, where energy becomes so evenly spread that no motion remains. A future of absolute quiet, not through explosion, but through the gentle dimming of all activity. Then we stepped into the Big Rip, where dark energy might grow strong enough to tear apart every structure, galaxies, stars, and even atoms. A dramatic, distant ending, a universe dissolving under the unstoppable expansion of space itself. Finally, Part 17 opened the door to other possibilities. The Big Crunch, vacuum decay, and microphysical transformations still beyond measurement. These scenarios, though diverse, all emphasize one truth. The future of the universe lies far beyond any timescale humans can grasp, stretching across periods longer than even the oldest stars will ever live. Now, as all of these stories settle into one continuous flow, the idea of a cosmic frontier becomes clearer. It is not only a physical boundary of space or time, it is the boundary of human understanding itself. The places we can reach, but cannot yet cross. The regions dimly lit, but still wrapped in the shadow of the unknown. And it is precisely the vastness of the unknown that makes the universe beautiful. If everything were already illuminated, wonder would fade. But because there are things we cannot see, cannot touch, cannot know for certain, every step forward in science becomes like lighting a small flame in the endless night. As the journey ends, it feels like standing beneath a wide night sky, looking up at distant stars. Space is quiet, infinite. Questions about the universe's beginning and end no longer feel unsettling. They become gentle currents of thought, like soft waves breaking somewhere far away. And in that moment, realizing that humanity is only a small part of the universe's story does not make us feel insignificant. It makes us feel connected to something far greater. From the limits of observation to the secrets hidden in the darkness of the future, from the CMB to the Big Bounce, from cosmic voids to the multiverse, this entire journey becomes a tender invitation to look at the world with open eyes. Not to seek a final answer, but to appreciate the beauty of the questions themselves. And as these reflections close, the mind can rest beneath a sky full of stars. The universe's mysteries do not demand to be solved tonight. They simply ask to be heard, to be cherished, to be held gently within human curiosity. In that stillness, imagination continues to expand, carrying us beyond every boundary, into dreams, into thought, and into every quiet discovery that life brings. Wishing you a peaceful night beneath the vast sky, where the universe's mysteries softly cradle every deep, restful sleep.